error budget, traceability. So we'll start off with everybody's favorite thing, and accuracy. I'll give you a chance to read this one. I like this one.
What should the jump translate?
Well, you can translate the word crap into anything that you don't need. So, let's see, a cart with square wheels. What's other things we don't need?
Facebook.
What's that?
Facebook.
Facebook, yeah. I do not need Facebook. So Facebook, basically Bob he's advertising and saying, my store is called, I have a store, I'm selling you everything you do not want. So, really bad tasting food, spoiled food, a roof that leaks. I have all of these things available for you. So his marketing is very accurate. So this is picking on both marketers, people who advertise, because they never tell you the truth. And also picking on us, people who do calibration, because we think that accuracy is always important. And it is. The sad little truth here, though, is I hope all of you go away and want to do really well-done error budgets. And I hope that you never encounter the situation that a person in the audience tells you that because your error budget, your error uncertainties are so large, we do not think you have a good method. And it's because everyone else in the room has done a bad error budget and is lying about their true uncertainties. But that is the risk you run. And trust me, it's much better to do the true science and it'll come out in the end. Stick to the facts, stick to the results. If you can show us that someone else is misestimating their uncertainties, you point that out in a nice fashion, in a careful fashion, and try to bring them towards a better uncertainty. But it always ends up happening when you start to compare results from different methodologies. And then that's where all of a sudden, and the gentleman that worked for me at the University of Arizona, we were doing round robins on reflectance of the reference panels. And his was the only one that actually matched NIST. And it was because his was an accurate uncertainty bar. All of the others, so his number differed by about 1% from NIST, but his uncertainties were 2%. So he matched. All of the other groups were claiming 0.2% uncertainties, but they were off by 2%. And then they all had to go back and redo their error budgets. And we tried to convince our guy to go back and redo his error budget, except instead of going from big to smaller, he just kept it big. So it's one of the reasons why that 2% uncertainty in the error budget discussion, in the reflectance, they were predicting it was going to go from 2% to 1%. His advisor thought that he could twist his arm and make him go from the 2% to the 1%. And I just said, no, that's fine, 2% is okay at this point. We'll wait until NIST changes their uncertainties, and then we can start changing what happens in the laboratory. So traceability. Traceability basically means that I have a pathway from some standard, and I'm keeping close track of that pathway. And I'm documenting it to the level that I know where all of my uncertainties are coming from, and I can trace from my standard all the way through to my final answer with known error budgets all along the way. And then I can combine them in the right fashion, and I can follow all the rules of what's called the guidance for uncertainties and measurements. Good go. If we do that, and I showed this earlier this week, I can calibrate a sensor in a laboratory. In this case, I'm showing a spherical integrated source that has been calibrated against a transfer standard, a radiometer, that has been calibrated against the primary standard of spectral irradiance. So somewhere, somehow, you can go to a metrology lab and you get an FEL lamp. And if you set that up, and in this case, go 50 centimeters from it, calibrate in irradiance mode, and then take that radiometer and flip it, and turn and look at the spherical integrated source, you calibrated the source, and then turn around and look at the source with your sensor, you are now calibrated, and you can trace your path to that spectral irradiance source. If I do that properly, someone else, someplace else, can buy a different lamp. If it's calibrated to the same standard, and it's spectral irradiance standard, it's an FEL, then they'll have the same uncertainty. And if they follow the same pathway, and they show that their radiometer behaves the same as this radiometer, or they can at least point out the differences and uncertainties, their sphere source behaves the same as the other sphere source, then I end up with a sensor that is traceable to that same standard. And these two sensors will provide data, looking in this case, this was Cindy's three-dimensional mineralogy map, so 15 ites in that whole picture right there. You'll get the same answer to within their combined uncertainties without doing anything to those data. They will automatically compare. That's the beauty of traceability. If those standards of irradiance are calibrated relative to System International SI standards, then you basically are now SI traceable. In the United States, we did not worry about SI as much as all we did was make sure we got our lamps from NIST. And then we were NIST traceable. And everybody who had a NIST traceable lamp should get the same answer. Even though if you bought 7 lamps from NIST that were all calibrated the same way, but maybe in different lots, some of them would disagree by up to 7%. Even though their stated uncertainties were better than 1%. And then there were arguments, and he stopped me to think about it. Well, in shipping, something happened with Philip. In operation, the lamp degraded. So these lamps would only be good for 50 hours of operation. There's all sorts of rules that come into this. The radiometer, maybe I'm using a slightly different wavelength measurement for this radiometer on the left and the one on the right. And that might cause enough of a difference in the calibration that no longer are these truly traceable to each other, because I'm not properly accounting for the change in wavelength of the source as it pertains to my transfer radiometer. So there's lots of places where you can follow traceability and get a different answer. Aster was traceable, not so much the standards of primary irradiance, but to a melting black body, melting point black body. So they were a radiant source, basically, that they were tracing to. And as long as they had the temperature scale correct and they knew what the output was, but they still ended up with a much larger difference in band 9 because of an optical crosstalk effect that was not seen in the characterization. So once we knew that we had the crosstalk, then we knew that the traceability had been broken. But until you had the data, you did not know that. That's one of the difficulties with this traceability concept. It's easier to find out when you do not have it than it is to prove that it's working, especially if you only have one data set. Now I wish I had put in, I hadn't, I deleted it because I always get sick of it. It's the curve that shows the solar irradiance as total solar irradiance as a function of time. The US has had multiple instruments to do this. The Europeans have had multiple instruments to do this. And for many years, we had solar irradiance. It was 1367 watts per meter squared. It was the solar irradiance. That's the standard number. And that was basically determined by ACRIM, active cavity radiometer for irradiance measurements. And they were launching ACRIM after ACRIM. So we had 3 of them. And you launched the first one, you got an answer. You launched the second one, and they agreed near perfectly. Launched the third one, they agreed near perfectly. Everybody was ecstatic. And then they launched the 4th instrument that wasn't ACRIM, it was TSIS. And it disagreed by more than the combined uncertainties. Guess who was determined, well, guess who they thought was wrong to start with? TSIS. It's 3 against 1. Traceability is not something where the number of votes makes a difference. Traceability is truth. It's basically you have to have a good uncertainty analysis. And the TSIS people, they came back and said, no, we've looked at the optical designs, and we are very confident that what is going on is there's a diffraction effect in Akron that is not in TSIS. And in fact, it accounts for about the right amount that you guys are talking about. And it's the same optical design feature in all three. So that would explain why there's a difference. And so NASA headquarters had to force the TSIS team and the Akron team to fight with each other over a 3-year period to get NIST involved to do measurements to prove without a doubt that indeed, because of the placement of an aperture in the Akron design, there was a bias. It was a bias that was larger than the combined uncertainties than their traceability showed. And it was until we had those two independent measurements that were truly independent with different optical systems that you can improve both of them. The TSIS people found some improvements they made to their processing that made their answer much better. Now we have a new solar irradiance, and I forget it, 1350 something, but it is now it's changed. The amount of output of the sun went down. It didn't, so it's not like we're going to cool off. It was amazing because there were articles in the newspaper about how now the Earth is going to cool because the solar irradiance went down. But it just was a change in the scale because of this traceability discussion. And it's similar to some of the things we've already covered in here as well. And I'm not trying to scare you, it's just the more we do this, the better off we're going to be because we'll find mistakes. So the reflectance-based method is traceable to reflectance. And that bothers a lot of people. And it bothers some of the metrology people a lot because they think there needs to be a SI, there needs to be a physical unit in there. And I can get that, I'll show it in a second. I'm going to use solar irradiance for that. But I can also use it in terms of I can do modeling. And as long as I can find a way to prove the uncertainties in the model, that's really where this traceability problem breaks down the reflectance-based methods. We have a radiative transfer model, we have a surface model, we have instrument models for the ASD, we have models for the panel reflectance, and proving that you know what the uncertainties are for all of those and that you can trace them back to some physical quantity is what has to be done to make it SI traceable. The debate will continue, but at the very least, in the United States, as long as we're using that PTFE standard, we're NIST traceable, and we'll let the metrology people help us over time to figure out how we can make that SI traceable. The solar radiation, though, is the one pathway, because the solar irradiance is traceable to the electric watt, depending on the methodology, but it all goes back to some kind of cavity radiometer that was looking at a source in one of the laboratories in one of the National Meteorological Institutes. So I just repeated again the solar curves for fun, but it's this traceability through irradiance. So once I multiply my reflectance-based results by the solar irradiance, I have an SI traceable value. The difficulty is trying to decide what the solar model is. We have a pretty good idea of what the total solar irradiance is. We have no good idea what the spectral irradiance is for the sun. And that then creates this problem of you get large differences between spectral bands just because that's solar model. So now, and again, we talked yesterday about, somebody asked the question, what's the uncertainty? What's the beauty is their error budget, their GUM says these agree to within 1%. Their uncertainty is 1%. Nobody is, the fun thing is anybody who knows how to do an error budget knows how to do traceability. I tell them that I have a 1% uncertainty because of solar irradiance. They'll ask, well, what about the SWIR? And I'll say, oh yeah, it's larger up there. And then they know that if they push it, then everything they're doing has to fall as well. So they leave it alone until we get it fixed. We all understand that this is hurting everyone from the metrologic institutes all the way through the solar measurement people and all the way into remote sensing. And of the group that's affected the least, it's the remote sensing community because we can just ratio it out and go to reflectance, and we're happy.